There are a lot of different sounds out there as well as in the studio, but they all have one thing in common. We can describe each of them by their spectrum of frequencies and by the way their spectrum changes over time. We are going to talk about spectra, therefore. About spectra, about their components, and about basic terms concerning the spectrum of a sound and the way they are confused from time to time. And when we talk about spectra, we will necessarily talk about wave shapes, at least about the most typical ones and their characteristics. Let me start with the tuning fork. I think everybody knows a tuning fork. This little helper producing a single note, the so-called concert pitch A4. Useful not only for choirs. Let's listen and look. The upper oscilloscope shows the wave, the lower one shows the frequency. Our tuning fork produces obviously a sine wave. The wave's frequency is 440 Hz. Well, of course, because the note A4 oscillates at 440 Hz. Here meaning the metal prongs oscillate 440 times a second to and fro. All right. And with that, we have discovered our first relation of wave shape and spectrum. The spectrum of a perfect sine wave contains only one single frequency. This frequency is the pitch of the sine wave. Sounds self-evident, but isn't. We will meet spectra containing frequencies which are not at all identical to the pitch of the sound. We are going to meet them quite soon. Indeed, we are going to meet them now. By the way, not every sound has got a certain pitch, of course not. Think of noise, for example. We are going to talk about noise later in this pro-seminar. But let me show you something which I used to call the opposite of a sine wave, a saw wave. I'll explain the term opposite of a sine wave a bit later. We see that there are a lot of frequencies in the spectrum of a saw wave, but only the lowest one, lowest in frequency but biggest in amplitude, determines the pitch. We need to get clear about some basic terms before we can continue and look at some details in the spectrum. We can divide the frequencies which we see in the spectrum of any pitched sound, for example a saw wave, into two functional groups. The first group has got only one single member. It's the lowest frequency, the frequency which determines the pitch of the sound. We call it the fundamental. Let me just mention that there are pitched sounds which deliver a perceived pitch different from the fundamental's frequency, but those special sounds are a matter of our regular courses at Modular City Junior High and at Modular City Senior High. The second group, which contains all the rest, the majority of frequencies, determines the timbre of the sound. The second group lets us perceive whether we are listening to a trumpet or a violin or anything else. All frequencies in this second group are higher than the fundamental's frequency. The frequencies in this second group are called overtones. Each frequency in the spectrum, included the fundamental, is called a partial. There is a special group of overtones which is called harmonic overtones. The spectrum of our saw wave here contains only harmonic overtones. These harmonic overtones are frequencies which are an integer multiple of the fundamental. 2 times the fundamental's frequency, 3 times the fundamental's frequency, 4 times the fundamental's frequency, and so on. But the spectrum of a sound can contain also overtones which are not harmonic ones, of course. Please beware. The term harmonic and not harmonic, or inharmonic, as some people call it, don't tell anything about the aesthetics of the sound. They are not at all related, these terms are not at all related to expressions like nice or not nice or musical or not musical. A harmonic overtone is simply an overtone of a frequency which is an integer multiple of the fundamental, strictly mathematical, nothing else. Let me demonstrate how changing the overtones changes the timbre, but not the pitch of the sound. I use an additive approach, meaning I add overtones to a fundamental or delete some of them or change their amplitude, the energy the partial carries. Let's have a look at some typical wave shapes now. We've already met the sine wave with its single partial. I called the saw wave the opposite of a sine wave and promised to explain later. Well then, the saw wave again. We see that the spectrum of a saw wave is very rich of partials in contrast to the poor sine wave. In classic In classic subtractive synthesis, where we have rich spectrum, which we shape using filters, what is subtracting frequencies from the spectrum, the saw wave is a common starting point, therefore. Looking at the saw wave's spectrum, we see that it contains every harmonic overtone of the fundamental. Well, the square wave now. We see that the spectrum of the square wave contains only every second harmonic overtone, only the odd ones. The even multiples of the fundamental are missing. And what about a triangle wave? Well, here it comes. We see that every even harmonic overtone is missing again, but the odd harmonic ones are present in the spectrum. The analyzer shows only a few of them here, but there are more at upper frequencies, higher frequencies. The difference between the spectrum of a square wave and the spectrum of a triangle wave is in the way the amplitudes decrease from partial to partial. With the triangle wave, they roll off a lot faster. Well, there are a lot more specific wave shapes to look at, but let it be enough here in this proseminar. We are going to talk about all of them in our courses later. But we have to talk about dynamic changes in the spectrum. Only the spectrum of a very simple electronic sound does not change. The sound of every classic instrument, a guitar, a violin, a trombone, and so on, changes during the lifetime of the tone, as well as do purely electronic generated sounds if they shall be interesting. and unpitched sounds, more or less noisy, or drones, or the sounds of natural or technical goings on, changes as well and follow an audible development. Let me demonstrate only two quite different examples here: a brass ensemble and the washing machine. Just watch the spectrum, how it changes over time, how partials step in and vanish, and how the amplitudes of the partials are permanently changing. The brass first. And now the washing machine. All right, let's attach an envelope to some of the partials of a sound then. But this was only a volume envelope. We can change even the frequency of a partial by attaching a pitch envelope. Let me show it. And you will have noticed it. By doing so, I've demonstrated the basic techniques of additive synthesis. The last matter of this pro-seminar is noise. There are some different, not really precise, categories of noise. Most common are white noise and pink noise. White noise covers the whole frequency range. The partials are randomly generated. The overall volume is more or less constant, but the amplitudes of each single partial, and there are such a lot of them, that it's nearly impossible to make out the single ones. They change randomly and fast. There are no spectral preferences. White noise is often used as a sample source for sample and hold units, as it delivers randomly nearly every possible value. Pink noise has a preference for the lower frequencies. It's kind of low-pass filtered, and the sounds of it are warmer than those of white noise. There are even more categories. You'll find expressions like brown noise or blue noise and others. All of them have different frequency preferences, but there is no clear definition of them. For example, the noise module I'm using right now has got a noise called radio. Well, that's all for today. You are well prepared to start our courses at Modular City Junior High now. Thank you for watching, thank you for being with us, and enjoy your day. Rolf.